Use implicit differentiation to find dy dx. Y squared plus 8x cubed equals 7y minus 9x squared. So this equation is going to be very difficult to rewrite in explicit form, which means I get one variable by itself and the rest of the equation is an expression in terms of the other variable. In those types of situations, it's best to use implicit differentiation to find the derivative, which takes advantage of the chain rule and assumes that the variable y is an outer function whose inner function is the result of that algebra that you would use to get y by itself. In that case, if y is an outer function, you would take the derivative of that outer function. In this, the derivative of y squared is 2y, but then you would multiply it by the derivative of the inner function, which is just dy dx at this point because we don't know what the definition of y is. 8x cubed, its derivative is 24x squared, and we just differentiate that as we would normally. This isn't an outer function, so we don't have to worry about the chain rule. Now we come across 7y. This is an outer function, so 7 times y, its derivative is just 7, but then we multiply by the derivative of the inside part, so we insert this dy dx term. And then we have negative 9x squared, differentiate that normally to 18x. And the last thing to do is to collect all of our terms algebraically so that we get dy dx by itself. So first thing, I'm going to move 7 dy dx to the left and 24x squared to the right. So 2y dy dx minus 7 dy dx equals negative 24x squared minus 18x. I will factor out dy dx on the left-hand side. And it looks like there's some common factors I could pull out here. It doesn't really matter if you do that or not, but it might be nicer if you at least pull out the negative. I think we can do better than that. I'll make it negative 6x. This would be 4x minus 3. And then divide the dy dx over. So negative 6x times 4x minus 3 all over 2y minus 7.